So we're going to be looking at how we can put vectors together, add them together, right? Not just finding angles between them, although the angle between them does come into this, but how do we add some vectors together? And the usual sort of objectives or goals here is going to understand the concept of the parallelogram law for adding vectors together, as well as the triangle law. They're both related, they both do the same thing. Understand the concept of a zero vector and find the difference between two vectors. And we're going to be able to represent a single vector as a combination of two or more vectors, something I think you've done in physics. And we're going to be able to apply these concepts to problem solving. So that's what all of this is meant to accomplish. So let's start off with the sum of two vectors, which can be found in one of two ways. To add the vectors, draw them tail to tail. So like the vector A and the vector B, again, remember you can use just lowercase letters to represent vectors. Usually the arrow is on top. I kind of left the arrow out just as a matter of convenience, but the arrow should be on each of these lowercase letters. So to add them, we draw them tail to tail and use the two of them adjacent sides of a parallelogram to draw the remaining two sides. So if I put this vector here, right next to this vector here, and then I fill out the parallelogram, that would result from that. So another vector B would be this line on top here, and another vector A with this line over here. So that would be how you fill out the parallelogram. Then the A plus B would be the diagonal that runs from the two tails to the tip of where the parallelogram opposite corner would be, right? So from the common tail to the opposite corner, this vector would represent the sum of those two vectors, okay? The parallelogram law is also used for subtracting two vectors. If you want to subtract vectors, that would be A plus minus B. It would be the same as minus B plus A. So what we would do is we would actually take B going in the opposite direction, and what it works out to be is the other diagonal. So this would be the diagonal that represents A plus B, and the diagonal that runs in the other direction, right? So from here to here, or from here to here, depending on whether you're doing B minus A or A minus B, would be the difference between the two vectors. So this would be the sum of the vectors, this line that I'm tracing out right here, and this one that goes between the two tips, right? That would actually be the difference between those two vectors. All right, so here's the triangle law now. Triangle law says to add two vectors A and B, then put them head to tail. So the one we did before was the parallelogram law, where we put them tail to tail and fill out the parallelogram and then take the diagonal of the parallelogram. Whereas this other method says put the two vectors right, tip to tail or head to tail. So here is vector A running from here to here. Here is vector A running from here to here. Here is vector B running from here to here. So the tail of this vector, right, goes on the head of this vector. So instead of you creating a parallelogram, you just say, if I started off here and then I went here, then from here I went to here, then this side of the triangle that goes from here to here represents the sum of those two vectors. In a sense, you're saying, I'm taking a trip from here. I'm going to go to this point here, then I'm going to go from that point to this point. But essentially what I've done is I moved from here to here. So that's what we call a triangle law. And it's like saying, what is the result of those two movements? If I went here, then really all I've done is gone from here to here. So that's my starting point and that's my ending point using the triangle law method. But just to be clear, both lines would still represent the sum. This dotted line here is still the sum of A and B. Whether I use a parallelogram or I use a triangle, I still have this dotted line representing the sum of those two vectors. So vector A plus B is represented by this dotted line. By putting the B vector at the head of the A vector and seeing where it ends up, and that would represent the ending point of the vector. The starting point would be the starting point of A. So if I'm adding the U and the V vector, for instance, and here is where I'm using the lowercase u and the lowercase v, then if this is u, I'm just going to go through the motion. Does it matter which one we use? No, it doesn't, because the results are both the same, by the way, Fernando. Can you explain the law again, the triangle law? I can, Kushi. Okay, so let me go back to that. Oh, wrong way. Let me go back to that. The triangle law And I'm actually going to show that to you in just a minute, by the way. But let me go back and just talk about the cushy for a minute. This vector that I'm pointing to here is the A vector, right? So take the B vector, shift it, and put it up here, which is what you're seeing in in this diagram over here, right? So what's happening is that, let me show you. I have an animation coming up to give you a better idea of that, but let me show what I mean. Take this vector here and move it so that it's now like that. So this vector has been shifted up, right? If you see what I'm saying, Koshi. And put at the so the tail of one vector is put at the head of the other vector and then creates a triangle from there because the third side of that represents the sum of those two. Does that, okay, great. All right, so let's move on. So now we're going to show this to you a little bit more, hopefully explicitly. So here's vector u, that's that vector right here. Here's vector v down here. So I'm putting them tail to tail, but if I've shifted the u vector over to this side over here, right? So this is the u vector. This vector is the same u vector. Remember, same direction, same magnitude. So I can represent the u vector as this vector over here. Then I can represent the v vector as this vector on top here. So the result, this is using the parallelogram law here. The result is still this vector that runs between them like that. So that's why this red line is the sum of those two vectors, right? So the u vector plus, and the reason it makes sense is because I can represent the u vector as this side over here. And look at the two directions. The directions from this vector to this vector, sorry, from this head to this tail are the same as this vector up here, right? So when I put this vector up top here, it's the same vector. When I put this vector over here, it's the same vector, but it creates this parallelogram. Then this diagonal represents the sum of those two vectors. Okay, now let's do u minus v. All right, so it's the same u, that's the u vector right there. This is the v. Now, instead of taking the v to run the way it normally runs this way, I can go in the opposite direction to represent minus v. So a vector that has the same magnitude but runs in the opposite direction would be the negative vector for v. So this vector over here now is my negative v vector. The vector on this side is my positive v vector. This is my negative v vector. So I'm about to try to do u minus v. So I'm going to go ahead and fill in some sides to represent that. So this is the u vector over here, same u vector over here. This is the v vector, the one running from here to here, right? So what's if you think about it, I'm in a sense, I'm saying I'm going from here. Remember, this is my minus v and this is my positive u. So I'm saying the minus v vector, and then it means I started off here. Think about it. I started off here, and I'm either going to go along the u line first, followed by going along the negative v line, which is this way. So I'm ending up right here. So here's my starting point. So this is my start. This is my end right there. All right, so that means that the resulting vector is this vector running from here to here. Okay, hopefully that makes sense. Let me go back. Going the wrong way. So the u vector is this vector, the v vector is this vector. That's a positive v vector. But no, the negative v vector is running the other way, running in the opposite direction. So if I now add some more lines onto here, putting another u vector here and another negative v vector up top here, it means that in a sense, I'm starting off here at this S, which is the start point. I'm going here and I'm going here. So it means that what my final track is going from there to there. That's what the u minus v vector. Okay. Now, how about if I wanted to, and this line over here represents the same thing, right? So it's another u minus v vector over here. So in a sense, it is saying I'm going this way first, and then I'm going this way. So really what I'm doing is I'm going eventually in this direction with this magnitude. Okay, and that's because I'm using this other pair of vectors to represent it. So instead of so in other words, I'm still going here, and then I'm going this way, and then therefore it means I'm going from here to here. All right. Okay, let's try it the other way. V minus u now. So remember, the one I did before was a u minus v. This is now the v minus u. So I'm going in the opposite direction. Opposite direction. All right, so here's my v vector again, my starting vector, which runs from here to here. Here's my u vector. So my negative u vector would be this vector down here, going in this direction, right? So I'm going to fill in the other sides now, right? That's my positive v vector again here. That's my, this is saying I'm going from here, down here, and across here. So really I'm going from here to here, right? So if I started off here, I went in the opposite direction of u, then I went in the positive direction of v. So it means I started up. So this is my starting point here. This is my ending point right here, right? And that's why the vector is running in this direction from here down. Now compare that for a second to the one before on the previous one. This one actually looks a lot like the vector that we're looking at, right? Yes, it runs in the opposite direction. So u minus v and v minus u are actually opposites of each other, right? They're the same magnitude, but running in the opposite direction. And also remember that the longer diagonal represents a sum. This vector represents a difference between the two vectors running in this direction. Now this one is running up and to the left, whereas if you look at the one that is going from v to u, this one is going down and to the right. Okay, so it's exactly the same distance, you're just going the opposite direction. And it's just like saying, if I had 6 minus 3 and 3 minus 6, I'm going to get the same number 3, but they're just going to have opposite signs, right? 10 minus 4 and 4 minus 10, both of them give you 6, but one gives you a positive 6 and one gives you a negative 6. So it's the same thing here, right? Both lines look very similar, like they're running, you know, sort of parallel to each other, but they're running in opposite directions. And it is the second diagonal. Remember, the first one, when you sum them, let me go back and show you that again. When we were summing them together, we got this diagonal right here. But when we're adding them together, we get the other diagonal going this way. In the same parallelogram, but it was the other diagonal, right? And that diagonal could run in two different directions. So if it's running this way, it means that you're taking the v minus the u. Okay, and I put another one there to represent the same vector going from up here to down here. Okay, I hope I haven't lost anybody so far. So the vector sum, a plus b, is sometimes called a resultant vector. Resultant meaning what you get when you put two vectors together. The vector that is equal in magnitude but opposite in direction is referred to as the resultant. The one that's opposite in direction is referred to as the equilibrium. So when you have two vectors that you add together, we call that the resultant. But the one that is equal to the in magnitude to the resultant, but you go in the opposite direction, referred to as equilibrium. Right? When you add two vectors together that are opposite, it gives you what we call a zero vector. So if I have a vector that runs, for instance, like this, and another vector that runs like this, they're both the same magnitude but run in opposite direction. If I add them together, I'm going to get 0, right? I'll give you an example. If you were walking, I know a lot of you have probably been to the airport or at least on an escalator or whatever, and you have those things that you can go on that move you along. I'm sure you've seen them, right? If you are on one of those things walking at, let's say, 6 kilometers an hour in one direction, which is opposite to the direction that that thing is moving in, they're just going to be standing still, all right? Because there are two forces that are moving in exactly the same magnitude, but in opposite direction. So you would actually not move at all. So there you go. So that's what equilibrium means. So if you add two vectors that are opposites of each other, you're going to get a zero vector. You can multiply a vector by what's called a scalar. And what that does is it either makes the vector get longer, or it still goes in the same direction, or actually if the scalar is negative, then it goes in the opposite direction. But if you multiply by a scalar, then you get a vector which has the same direction, but it has a magnitude which is bigger than the vector it had before, or smaller if the k value is in fact less than 0. Okay, or sorry, the k value is somewhere between 0 and 1, and you can actually make the vector get smaller. But all a scalar does is just change the magnitude of the vector, but does not change the direction unless it's negative. Okay, so here's a little graphic that shows you how we can add some vectors together. And I'm just going to play the graphic so you can see exactly what it does. I'm going to take vector A, which is this vector right here. I'm going to add it to two B's. I'm going to take two of these B's. I'm going to add two C's onto that. And we're going to, from that, see what the result is of all of this. So here comes a little graphic that hopefully you can follow along with. So remember, 2b means that I'm taking 2 times the length of b. So b is going to get twice as long, but still going the same direction. I'm going to do the same thing with the c. The c is going to be twice as long running in the same direction. A is not affected by any scalar. So here we go. So there's A, which is approximately 3 units going up. There's the B, which is going down and to the right. I'm going to take another B and put it on that the head of that one. Then I'm going to take 2 C's. So that's C number 1. And this is C number 2. So if I wanted to know what was the actual track of all of that, if I wanted to figure out what was the vector that represented that, it's this blue line right here. Because my starting point was when I put that first A vector there. I know you can see that the ending point is where I get the head of the final vector when I added those 2 C vectors. So that would be a sum of those 3 vectors. 1 of the A's plus 2 of the B's plus 2 of the C's. Okay? All right. Let's go on to the next slide. Oh, I'm hoping that that graphic made sense. I'm going to go on to the next one. Okay, so I'm going to be doing some minusing as well for this one. I'm going to take the A, the 2B, 1C, I'm going to minus a D. Now, D runs in this direction from left to right. So my minus D would be the same distance, but running in the opposite direction. So let's see what that looks like when I sum all of those together. There's my first A. Then I'm going to take 2 of the B's. It's the same B like what we had on the previous slide. That's 1 B there. This is the second B. I'm going to add 1 of the C's now. All right, not 2 C's at the last time, just 1 of the C's. I'm going to minus a D. So there's my minus D. Remember, D runs from left to right, but my minus D runs from right to left. So that would be the sum of all of those vectors. That blue line, again, represents the sum of all of those vectors. So from the starting point where I put the first A, from the head of the first A to the tail of the final minus D represents the track of this whole sum and difference of all of these vectors. Hopefully the graphic makes sense. Okay, so how can I represent a single vector as a, think about what I just did, and how can I represent a single vector as a combination of vectors? So think of OA as being A, and it's labeled on the diagram. So this is my A vector right here. That's my OA. So O to A can be represented by lowercase letter a with the arrow on top. OC can be represented by a B vector. That's running from O to C. And OD runs from O to D, and that's lowercase c right there. So let's see if we can put together a bunch of vectors to represent things like, for instance, the BC line. Okay, now BC, remember, look at the diagram, runs from B to C. How can I go from B to C using only vectors A, B, and C? So you know I'm going to turn that over to you now. Look very carefully at the diagram and see if you can come up with a vector to represent movement from B to C. Think about how you can add or subtract or put some vectors together that's going to make that work. So I'm getting minus A from Adam and from Vanessa, right? What do other people think before I chime in on that? Okay, Fernanda says she agrees, all right? Come on, I want to hear other people's, and Tamalea also agrees with that. Anybody else? Come on, folks. I want to see at least 2 more people chime in on that. I'm not saying it looks right. Okay. All right. Okay. Well, let's see if it is right. I want to get from B to C. B runs from here to here, but the A vector doesn't run in the same direction. A vector runs from O to A. So if I want to get from B to C, it's the opposite of the A vector. So yes, that would be my minus A vector. Can it be positive? No, it can't be positive, because if it was positive, then we're going from C to B. Do you see what I'm saying, Ariana? So if you use A, that means that you're looking for the CB vector, not the BC vector. Okay? All right. How can I get the GF vector now? Can anybody suggest a way that I can get the GF vector? Let me hear what you got for the GF vector. I see some answers. I see Fernando and Vanessa thinking it's A. And Richard also thinks it's A. Right? And Kush, look at that. All of you people just hope you're not just following each other here. Hope that's not what's going on. No, it's A. It's A. Well done. It is A. Right? So now you're looking for a line that is the same direction as the GF vector, and that would be the OA vector, which is what we're calling A. So that's fine. The OB vector, you want to go from O to B. Now, obviously, you need to sum some vectors this time for that to work. All right, so I'm seeing from Fernando B plus A. I'm seeing B plus A or A plus B. A plus B. I'm seeing some A plus Bs. Well, I'm going to have to agree with you on that. It is A plus B. And the fact is that if you put A plus B or B plus A, you have the same result, right? The fact is that just like how in regular numbers, addition is commutative, which means the order in which you add together does not matter. Yes, Danny, you're right. Then the order in which you add vectors together actually doesn't matter either, right? Vector A plus B is the same as vector B plus A, right? If I'm trying to get from O to B, I can trace this out. If I want to go from O to B, I can either go along A and I can take B, or I can take B first and then A. It still goes, this eventual track still goes from O to B, right? AC, look at AC now. Let's see if we can come up with a way to get AC. Okay, Jordan is immediately out with an answer. She says it's B minus A. What do other people think? I'm not going to agree or disagree with yet. Hold on, I saw, oh, there were some other answers. Kushi thought it was A plus B. Vanessa said B minus. Okay, so, oh, there's a whole bunch of answers here. B minus A, B minus A, B minus A, then A plus B, so B minus A. So most people think it's B minus A, probably because it is B minus A. All right, so I want to be sure, Kushi, you see why it's B minus A now? Does that answer make sense? Just want to make sure that you're clear on that. B minus A, or should I sort of spend a few minutes on that first? Can you explain the difference between OB and AC? Okay, so OB goes from here to here. AC, all right. Okay, so OB would be a line that runs from O to B, right? And that is probably the same magnitude, but a completely different direction from A to C. Because if you can think, look at where my hand is tracing out right now. O to B means I'm going from here to here, whereas A to C goes from here to here. So they actually cross each other. And two vectors that are equal are never going to cross each other if they're equal. They can coincide with each other like they'll be in the same place, but they're never going to cross each other because they either be parallel or they'll be in the same place. Do you see what I'm saying, Kushi? They can't be the same. OB and AC. Okay. All right. BG. Can anybody say a way that I can get B to G? All right, I'm seeing a bunch of C minus A's here from Jordan and Ashvan and Vanessa and Richard and Fernando. She puts minus A first and then the C. And that doesn't matter, by the way. Again, as long as the A is negative and the C is positive, then we're good, right? So C minus A makes perfect sense. So Fernando is absolutely correct as well, even though she put the minus A first, right? So you're trying to get from B to G. From B to G, we can either go minus A first and then add on the C, or as some other people did, we can put on the C first and then minus A. It doesn't really matter. You end up in the same place anyway. And finally, from O to F. So I'm getting A plus B plus C. So Richard and Ashvan and Vanessa think it's A plus B plus C. Are they? And Vanessa as well. Is that what everybody else thinks? Are you really going to agree with that? Do you really think it's A plus B plus C to go from O to F? Yeah. Okay. All right. That doesn't work anymore, I guess. To go from O to F, I guess you can go along A, then you can go along B, and then you can go along C. All of these are positive. This is a positive, This is a positive because I'm going from A to B, which is the same thing as from O to C, and this is also positive going up. So it is in fact A plus B plus C. Absolutely, Fernando, Sarah, Thomas, Vanessa, and everybody else who is clearly on the money here. Okay, now let's spend a few minutes looking at how we can add vectors that have actual numbers on them. All right. This is the kind of thing. We're going to be doing some more of this as we go through this course, but here's an introduction to it. Two forces are pulling an object, and we're putting those two forces tail to tail, right? It says that F is pulling the object south, right? So that's the first vector here, the F1 vector, and it has a magnitude of 10 newtons, right? So it's pulling south at 10 newtons. F2 has a magnitude of 20 newtons from here to here. F2 is pulling the object in the direction of north 23 east. And we talked about that when we did this in the first session. North 23 east means I need to be 23 degrees east of north. So east is over here. So if I am east of north, I'm 23 degrees away from north. Another way that we could have said is to put 0, 2, 3, because remember we said that we could use a 3-digit number and measure from north going in a clockwise direction. So I could have done it that way as well. Find the resultant and the equilibrant. And I remind you that the resultant represents the sum of these two vectors. The equilibrant represents the vector that would be the same magnitude as the resultant, but goes in the opposite direction. So let me walk you through what that's going to look like. So what I'm going to do is I'm going to first of all find another vector that I can put up here to represent the vector F1. So this is the vector F1 here, but I'm putting it up on the top here, and I'm going down because it is 10 newtons going down. And I'm going to put another vector over here that goes from here to here to represent the same thing as F2. So both vectors that I just put in, I'll go back. Oops, sorry, wrong way. I'll just go back again. The two vectors that I'm putting in, right? These two vectors are tail to tail. And there's another vector I'm putting in here, another vector I'm putting in here. So this line here, using the parallelogram law, I don't know why I have such difficulty saying that word. Using the parallelogram law, that vector right there should be the sum of these two vectors. So we're going to use some trigonometry to find that, right? Maybe you can think of how that would work. This angle right here is 23 degrees, by the way. So what that means is that we're actually going to see if we can, when we find the resultant vector, sometimes you give that vector as with reference to one of the pre-existing vectors. So we can think of that as being our theta right there. So what we're going to do is we're going to say that, excuse me, this is, and hopefully you all remember the cosine law, right? The cosine, and this should look familiar to you, that this side here, this side here, remember, is the 10 the 10 Newton line, and we can use the 10 as being the magnitude of the line, and the 20 Newton line right here, right? And when we're using the cosine law, then we say that we take the two, and the angle between them would be this angle right here, by the way. We're going to be taking 10 squared plus 20 squared minus 2 times 10 times the angle between them. Now, why are we taking 23 degrees as the angle between them? Can anybody see why that might be if we're trying to get the length of this side right here, right? Does that sort of make sense to anybody? Does anybody see why this would be the length of this line that we're trying to find? If this angle over here is 23 degrees, right? Well, I'll show you why. If you remember the cosine law, well, not the cosine law yet. If you remember your alternate angles, if these two lines are parallel, this line here, or this line right here is parallel to this line right here, then it means that if this angle here is 23, then it means that this angle up here will be 23 degrees as well. I want to make sure I've never seen this equation before. Whoa, Adam, okay. It's a cosine law equation. Does the phrase cosine law even ring a bell for you? Let me start off with that. Have you heard about the cosine law? There's a sine law, there's a cosine law. Does that ring a bell from you from maybe no? Wow, okay. All right. Well, here's a good time for you to get to know the cosine law. It's grade 10. Yes, it is grade 10. Right? And I just want to point out, all right, let me erase this first. Let me just go ahead and erase this first. So what I'm trying to point out here, go back to the pen. Okay, what I'm trying to point out here is that we can use the cosine law. I'm rusty on the laws. I didn't think it is in advanced functions. No, you wouldn't have, because it's not something that it was covered in advanced functions at all, but it was covered in grade 10. So there's a sine law, which we're not using now. We will be using a sine law at some point, but the cosine law is the one that we're using now. So folks, you're gonna have to find some way of, if you never did this before, to try and do some catching up on that. Okay, but anyway, the cosine law says that if you have a triangle where you have what's called the included side, and I'm talking about this included angle rather, I'm talking about this angle right here. Hopefully this part of, let's do this. Hopefully this part makes sense. How do we know we have to use the cosine law again? You use the cosine law. That's a good question, actually. You use the cosine law when you have two sides. First of all, it's used when it's not a right triangle. You don't need the cosine law if you're doing a right triangle. It's used when you have two sides and what's called the included angle, right? So if I give you an example, let's just draw a quick triangle right here. Let's say this angle here was 35 degrees, and this side was 10, and this side was 25. And what you're trying to find, I put as a dotted line. Let's call that side X, right? This is when you use the cosine law. So we'll talk about the sine law on another occasion, but anytime you have two sides that you know, so these two sides are the known sides, the 25 and the 10 are the known sides, and the angle between them is 35 degrees. That's when you use a cosine. That's one of the times you use a cosine law. The other time you use a cosine law, since you're going over it right now, is when you have all three sides of a triangle. So let's say this is not a right triangle. I just made this triangle up. Let's say this was 12, this was 14, and this was 25. I could use a cosine law to find out a missing angle. And I wanted to know what this angle was. I'll call this angle theta. So I could, this sounds familiar. Okay, good. So I could use a cosine law to figure out a missing angle if I have all three sides, or if I have two sides and what's called included angle, then I would use the cosine law. Just so you know, the cosine law is useless in a case like this. Let me show you when the cosine law is useless. Let's say I had this side as being 17 and this side as being, I don't know, 22. And then I was given this angle over here, right? So let's say this angle over here was 100 degrees, right? I cannot use the cosine law there because the angle that I have is not the angle between the known sides. Okay? So Adam is now saying this sounds familiar. That's good because it should be. So this one that you're looking at now, the last triangle I just drew, would be a case of the sine law, not the cosine law. We need to be able to use both for this course. So let's come back. Let me erase all of this now and come back to what we're working on here. All right, so I'm going to take away all of this. Take away all of that. And for your homework, you don't need this. Actually, I think you might. You may need this for the homework. So it's a good thing that we're going over this right now. And let me go back to this. Okay, here we go. So the reason that I'm able to use the cosine law, Hall pass, Kushi says, okay, Kushi, 5 minutes, please. The reason I'm able to use the cosine law is because I have two parallel sides. I have what's called a transversal. So this angle here is the same as this angle over here. which is what we have here. We have these two parallel sides. This side here and this side here is parallel. Excuse me. This is the transversal, the line that goes between the two parallel sides. So if this angle here is 23, then this angle under here is also 23. And that's the angle between these two sides. That's what this is, and that's what this is. These are the two sides that are the same. Not the same, sorry. These are the two sides that we know. This is 20, this one here is 10. Remember? All right. So now we can use this cosine law, right? So x squared, which is the length of this side, is equal to the 10 squared, which is this side, plus 20 squared, which is this side. Hopefully you can see what I'm pointing to, right? Minus 2 times 10 times 20 times the cosine of the angle between them, which we already said is 23 degrees. So that's my 23-degree angle right there. Right? That's where my 23-degree angle is. Where does the 2 come from in the cosine law? It's part of the cosine law. Let me write down the cosine law equation for you. I see a lot of people have forgotten this. The cosine law says that a squared equals b squared plus c squared minus 2 times b times c cosine of a. That is the cosine law, sir. It is part of the equation. Okay, so the minus 2 is not something that is unique to this particular case. It just comes from the cosine law itself. All right, so let me go ahead and erase that as well. Actually, it says erase all ink, and I didn't see that choice before. That's much easier. And let me go back to the pen and then take off the pen. Okay, so all we're saying, and I'm just going to put the the 23 degrees back on here, is that this angle here is my 23-degree angle. And I want to remind you that I know that because of the fact that this line here is parallel to that line there, and this line runs between them. So 23 here is the same as 23 up there. Okay? All right. Find the resultant. Resultant is the length of the dotted line with the X mark beside it. And we already figured out that that's 23. So here's our cosine law at work. Okay? So let's just follow this through now. It should be equal to approximately 11.48 degrees. And that's newtons, by the way, not degrees, but newtons, because we're measuring all the other ones in newtons. Can I ask you to try that on your calculator right now, please, on your own? Right? Get some practice with this. 10 squared plus 20 squared minus 2 times 10 times 20 times the cosine of 23. That's x squared. And then, of course, you also have to square root that to find the length of that side. Okay? So can you do that for me now, please, on your calculator, and just confirm that you're getting the same thing that I got, 11.48. Right? I know I have my, my on virtual calculator. I can show you how to do that, but let's see if you can do that on your own. All right, Richard and Ariana said they got that as well. And you should be trying this for yourself, not just depending on me, because clearly I made mistakes, as I have in the past. And I will continue to make mistakes as I go forward. Let me just tell you that. So you need to back me up, folks. Check it out for yourself. Got the same thing, Danny says. Okay, good. And how about everybody else? Did you try this for yourselves? Or are you just sitting there passively looking at the computer, playing on your Xbox? You got to make sure you're actively involved in what we're doing here. So, okay, Ashwin says got the same thing. Okay, great. All right, so that's not the whole answer, because that is merely the magnitude of the result. Remember, the result is the vector that runs between them, right? That's the vector, that's the dotted line. But we also have to give the direction for us to say that we have the answer. So this angle right here is going to be important for us to get that direction. So the resultant force is 11.48 newtons. Now, here's where the sine law is going to come in. I said to you before that sometimes you need to use the sine law. Well, the angle that's marked as theta in the diagram, right, is the angle that I'm trying to find. And hopefully you'll see why in a second, because once I find that angle, then I can use that to figure out what the direction is using the directional bearings that we talked about before. So the sine of theta over 10 So the sine of this angle here over the side that's opposite to it, which we know is 10, this is 10 right here, is equal to the sine of 23, which is this angle up here that we just got, over the size of the sine of, the length of this side, which is 11.4, which we just got, right? So if you put all of that together, in fact, why don't you put that all together and tell me what you get before I press the button, right? I'd like to see everybody try this for themselves. Sine of theta over 10, right? Go back to grade 10 for a bit and see if you can get what the angle theta is. At some point, you will have to use the inverse key to get your answer. So folks, over to you. Let me see you all put that in the chat. And I don't want just one person put in the chat and everybody just says, yeah, that's the same thing I got. Because I'd like you to work it out for yourself. All right? Work that out for yourself. Right? You should be cross multiplying and then you should be finding the sine to the minus 1 of something that gives you the theta. Come on, folks. Let's do this for ourselves. Everybody. And let me see some answers popping into the chat so that I know that you know how to do this. What is the size of theta? I see no answers so far. Is that nobody knows how to do this? Okay, so I'm getting from Vanessa and Carly 19.9. 19.89. Okay, and Javier, Richard, Danny has a different answer though, 19.89. Oh, sorry, same answer as everybody else. Yeah, sorry. Yeah, okay. All right, so 19.9 approximately is the correct answer. But that's not the answer that I should give, just saying. Because remember that I need to add that to 23, right? Remember, this was given as being north 23 east. I have to give an answer like that. So that would be 43, and therefore north 43 east is the direction that this particular object would be going in when you are pulling with those two forces with this angle for the 20 Newton force. Okay. All right. Hopefully that. Thank you very much, by the way, all of you, Richard and Javier and Danny and Carly and Vanessa. All right. Thank you. So the resultant force is, or the direction of the resultant force is north 43 east. But the question asks one more thing, which we haven't answered yet, which is the equilibriant. The equilibriant, remember, is the same force, but the direction is just the opposite direction. So the force was, where's the force now? Where's the force? 11.48 newtons. So it's the same force, but now instead of being north 43 east, it's south 43 west. So that's the only difference for the resultant. Okay? All right. F1 has two forces are pulling objects. So again, same kind of question. We're going to give a different way of going about it now, because now we're talking about giving the angle between those two forces. So F1 has a magnitude of 7 newtons. So that's this line right here. F2 has a magnitude of 11 newtons. That's this line right here. The angle between F1 and F2 is 135. So that's this line right here. Find the magnitude of F1 and F2 and describe its direction relative to F1. Okay? All right. So we didn't get a bearing, which is what we got in the previous question. I'll take you back to that. We got a bearing on this one, the 23-degree bearing. Now we're saying that we have two forces, 7 newtons and 11 newtons, that are acting on a common point. So they're tail to tail. The angle between them is 135. And we want to add these two together. And adding them together would give us this third side, or the diagonal of a parallelogram. So we need to figure out what the length of this line is. Well, what you see me doing here is using a principle in geometry which says that in a parallelogram, two adjacent angles are what's called supplementary. So if this is 135 between them, then the angle that is in the corner, which is right across from, by the way, the angles that are across from each other are the same, but the angle that is adjacent, right next to it over here, right, those are supplementary, which means they add up to 180. So if this is 135, this is 45. And that's useful because now we've created a parallelogram where there's a 7 Newton side here. This line that I'm tracing out right here, that line represents the 11 Newton side right there. So now we have a 45 here, right? Angle between them, a 7 here and an 11 here. We can use the same cosine law that we just used a few minutes ago. Okay? The angle between them, though, is not, the angle between them is 135, but we use a supplement of that. We don't use a 135, we use a 45-degree angle because that's the angle that would represent an angle that's between the two vectors when you go from the tail of one to the tip, and then from the tail of that to the tip of that, that would represent the sum. That's like the triangle law at work here. From here to here, then from here to here means I'm going from here to here. And this side is across from the 45-degree side angle. And that's why we're using that as the angle to represent or to put into the cosine law. Did that make sense? The fact that we're not using the 135-degree angle, using the supplemental angle is important for us to get because this comes up again quite a bit when we're doing calculations like this. So you're given an angle between two vectors. You're given the magnitude of the two vectors. You're asked to sum them. You don't use the angle between them. Use a supplement of that angle in the cosine law, which is exactly what we're doing right now. So I'm going to turn it over to you now and ask you to tell me what the length of that side is by just simply putting that all into the cosine law equation. I'm going to wait patiently to hear from you. What's the length of side x? So you're just plugging all that information into your calculator and taking a square root. That's all it is. That's all it is. Vanessa, you have a number for us yet? If you don't, we can give you a few minutes. Vanessa? 7.8 newtons, she says. I get 2 decimal places, but absolutely, well done. But now we also have to give its direction relative to F1. So here's what we need. We need this angle between the, and thank you very much, that was well done. We need the angle that goes between these two right here. So when I give an answer, I'm going to say it's 7.8 newtons and this number of degrees from F1. So we're trying to find this angle right inside here. Can anybody suggest a way I could find that angle? Let me mark it off on this thing as to what angle I'm talking about. Right? I'm trying to find this angle right here. Remember, 135 goes all the way around between the two of them, but I'm just trying to find one piece of it. Can you suggest a way that I could do that? Anybody? Is there some trigonometric strategy that could be used to get that? Anybody out there sees a way that we can work that angle out? We have enough information right now to do it. What can we use to do it? Anybody? Nobody sees a way that we can do this? Well, it's the sine law. Oh, by the way, this 7.82 is the magnitude, as you said. Here's the sine law. The sine, remember, of theta, which is this angle right here that I'm pointing out now, that over 11, I know this is 11, excuse me, because it's the same as this one over here. The sine of that over 11, thank you, Tomaleo, is equal to the sine of 45 over the side we just got from Vanessa a few minutes ago, 7.82 or 7.8. She gave us 7.82. So this is what I'm asking you to work out now. The sine of 11, the sine of theta, I would ask one of you for that in a minute, over 11 over this side is equal to the sine of 45 over the length of x, which we now know is 7.82. So everybody, work out what that theta is for me now, please. Thank you, Vanessa. I'm taking it out of my selection wheel here. I want to ask one of you now for that answer. You should all have your calculators. You should all be ready to go. And I also have a name ready to go. Maybe I'll show you who that name is in a minute. But anyway, let's keep this going. So Tomaleo is right. It's a sine law. Right? So you see, I told you at the beginning of the class, there's a lot of trigonometry involved in vectors. A lot. Okay? So if you need to brush upon your trigonometry skills, now would be a good time to do that. Okay, so Richard, somehow your name came up. So Richard, first of all, let me ask you to check in for me, please. Oh, look, he has an answer already. All right. So 84.1 from F1 is that magnitude, is that direction. Thank you very much. You have 84.07. 84.1 is what I have, but that's obviously the same thing, right? So there's my complete answer. I've gotten, it says find the magnitude of F1 plus F2, and that magnitude of F1 plus F2 is 7.82 newtons, and it's 84 degrees from F1. So that's one way to write it. All right, I think this is the last one. Let me just see here. Oh, well, no, let me go ahead and just set it up. So plane is flying in calm at a speed of 420 kilometers per hour in the direction of 291. So what that means, remember, is that when you are measuring from north all the way around, right? So 291 means that you start off up here and you're going all the way around until you get up to here. That's what 291 means. In the direction of, oh, I'm revealing too much, sorry. It encounters a wind blowing from the north at 50 kilometers per hour. So the wind blowing from the north is this black line right here. So here is this vector representing the 291. Here is this vector representing, not the 291, the 420 kilometers per hour. Here's this vector representing the wind blowing from the north at 50 kilometers per hour. Find the plane's resultant ground velocity. So if you think about it, this line down here, right? So I could put the, again, I'm filling out the parallelogram for this. So this original line represents the 291. That's your 291 right there, right? And then what I'm doing is I'm superimposing on that now. And that, by the way, is the direction, but it's 420. So this distance here is 420 kilometers per hour. So I'm going to put another 421 down here. That's parallel to that one. So I can fill out my parallelogram. And my line that's going north, south, going from the north means it's going south, by the way. So it's going south, going from the north, it's going down. So it's the plane is trying to go this way, the wind is trying to push it back this way. So this line here, this dotted line represents the ground, the plane's resultant velocity. So remember, no, this whole circle here is my 291 degrees. That whole thing is 291 degrees. So let's see how we can set that up using the cosine law. The reason can anybody see why I'm using 69 as the angle that we're going to be using? Can anybody see where that 69 is coming from? Using the information that we have there, can you see where 69 might be coming from? Remember, we're trying to get the length of this dotted line. That's our goal right now. Can anybody show me? Can anybody illustrate? Can anybody figure out 360? Okay, so that would mean, and by the way, 360 minus 291 does give us a 69, which means that 69 would be this angle on top here, which is the same as this angle up here. That's the same principle that we talked about before with the alternate angles. So the angle that we're saying is between those two lines is the 69 degrees that we're talking about, and that's the one that we want to use to find excuse me, to find the resulting distance or speed rather. All right. So the 50, which is this line right here, the 420, which is this line right here, angle between the two of them is the 69. That would give us the length of this line right over here, which is what we're trying to find. That's the resultant velocity right there. They didn't give us the angle between them. Now, we could have worked out the angle between them, just so you know. Right, here's another way we could have got that. How do you get 69? All right, let's do it another way, Tomadale. Let's do it another way. What would be, let me erase something here. Let me do it. Let's do it another way so that we can, let's do it the way we did it the one before. All right, so what I'm going to do is I'm going to erase all of that. Now, let us consider this from here to here as, oh, sorry, that's wrong. That's wrong. Let me fix that. Let's consider from here to here as being 291. Can we start with that, Tomadale? Okay, does okay, good. Now, what is the angle between these two vectors? So meaning, what is this angle right here? Let me just measure this part, just this part right here. What is that angle right there? Can you get that angle for us? How would you get that angle, by the way? Can you get that angle from, is there a way to figure out that angle, Tomaleo? See, a lot of this is sort of going back and thinking through the stuff that you did with geometry. Can you figure out a way to get that angle that I just colored in, the blue, the red angle right there? Because that's the angle between the two vectors. Is there a way to get that angle? The whole thing is 291. 291 starting from north, going all the way around. Can you figure out a way to get that angle? Can't think of a way to get that angle there? Just between those two, between the red line and the black line. Can you think of a way to get that, Tommy Leo? No? Well, put it this way. From here to here is 180, correct? Right? From north to south is 180. All right. So what's and the whole thing is 291. So if we stop here, we'd be at 180. But what about the part that goes from down here to here? The whole thing is 291. Right? So what is that other piece that makes it up to the 291? What do you think that is? How much does that work out to be? Work that out for me now, please. The whole thing is 291. So starting from north and going all the way around, it'll be 291. Okay, which is what? Okay, 111. So that means that the angle that is between these two is 111, correct? Now, if this is 111, what is the angle that is over here? It's a parallelogram, right? And we just said this in the previous question. It's a parallelogram. Then two adjacent angles are supplementary, which would mean that that would still be 69, if that makes sense. Okay? Still be 69. So that's another way you can get that 69. All right. So we're running out of time here, folks. So let me erase all of this so we can finish up this question. So what that means is that we can now use the cosine law. So x squared is equal to 50 squared plus 420, etc., etc., etc. I need to get that number from you to get the plane's ground velocity. Did we do this number already? I don't think we did. All right, so very quickly, work this out. We can always finish this up tomorrow. You have enough information now, by the way, to do the homework, just say. But can I get someone to tell me what this velocity is, which will be that dotted line? And that's somebody I'm going to be asking is Kashaf. Kashaf, you are there, right? You're there with us, right, Kashaf? Usually you are. Can you tell me what that x is, please? When you do all the math on that on your calculator, what does that work out to be? Because that answer you're going to give us now is the velocity of the plane, right? The plane which was going at 420 is going to be kind of slowed down by this wind which is blowing it south, going from the north, it means it's blowing it south. Go ahead and work that out for us, please, in the 2 minutes that we have left. 404.1 is I got 404.78. I don't know if our calculators are a little bit off. I don't know. What did other people get? Am I wrong? I could be wrong. I could be wrong. 4.78, yeah. So it might be a little bit off there, Kashaf. Maybe you're rounding, but round a little bit different. That's all right. It was not. Which hopefully, if you're a pilot, that could be that you could end up in the wrong city if it was that much of a difference. By the way, anyway, that's the speed. And very quickly, I'll just show the last part of this so we can finish this up. To get the direction, I'm going to find the sine of theta, and theta would be this angle right inside here is what I'm going to be actually trying to find. So that's this over 50. Remember, this is 50 right here, right? And this side we just said was the the 404 point whatever it was. So if that is 6.4, then we can take the 291 minus 6.4 to give us 284.4. We can go over this some more tomorrow just to finish this up, but I just wanted to make sure we squeeze this in there. And of course, it will be on the video that you can review later on.